Welcome back, everybody. For this video, I want to go through something that seems very low level, something we probably handled in middle school, maybe even earlier. It's the idea of substituting. Substituting for what? Well, for variables. It's surprising how easily this gets off the rails. Despite all our practice with it, we can be fooled. So I'm going to start with a fable. Every day, Haskell Curry and Curry-Feys would go to lunch at Constance. The menu was always the one posted item. On Curry days, Haskell was happy, but Robert would be sad. On Fridays, Robert was delighted, but Haskell was mad. Then one day, the two of them had an idea. Replace the menu with a variable, and they could both order what they wanted. How did Curry and Feys hack the Constance lunch? The premise is that Constance only makes one product. And so whatever is the one item on the menu, that's all you could order. And yet, they managed to get what they wanted because they substituted for the menu a variable, and now they could replace that with anything they wanted. There's something that's not right about that. To really understand it, let's look up close at something we understand mathematically instead of the fable. So let's look at the constant functions. When we graph these, if we have y equals 2, that's going to correspond to a function that we would graph on the horizontal axis at the line height 2. The reason for this is that every input comes back as 2. So as we move along the x-axis, we never see a change in altitude. We could change the name of the function to f of x, and we could set that equal to some other number like 3.14, perhaps the one in green. We might have in mind that that's supposed to be the actual digits of pi, and that goes on forever, and we could substitute it with the variable name pi to know that it means the actual constant there. In fact, we could use any constant c, and we could describe all constant functions in a uniform way. Like here, we could call them k sub c of x equals c. This tells us that we know that they're all part of one family. They all have slope 0. So what's going to be the trouble? Well, do all constant functions have slope 0? Let's try the Curry-Feys hack. See, c in k sub c of x is the placeholder for some future choice. What Curry and Feys did is they chose c to be x. And now we see the genius of their method. They took the constant function, and by replacing c with x, they have k sub x of x equaling x. If we graph that, it's just the line y equals x. It has slope 1. This is how Curry and Feys hacked the soup fry conundrum. This can't be right. A slope of a constant number cannot be 1. But what's really going on? What is explaining that this behavior was possible by substitution, but seems impossible from logic? The real truth is that substitution isn't just replace all symbols. There are rules to substitution. And the trouble is, when you introduce rules to anything you're doing, you're minimizing what you're allowed to do, and you're choosing clear logic. So we have to come up with a logic for substitution? Yes. And it's been done for us. Not only did Curry-Feys work on the formal rules, but this is now known as the lambda calculus by Alonzo Church. Lambda here is the Greek letter lambda, which you see as this symbol like this. Looks like an upside down Y, but it's red lambda. This is the lowercase version. So let's do a quick refresher on what it would look like to write down the rules of substitution when they were just the generic obvious ideas that we knew from primary school. The first one is the identity law. If I have a variable x and I want to substitute in a string of symbols, sigma, I should just get sigma back. By the way, throughout these slides, x will be a variable, a will be some constant, and sigma will be a string of these values, along with one special arrow that we'll get to in a minute. The key thing here is that variables are defined as variables simply by being in their own alphabet of variables, and constants are constants if they're in a separate alphabet of constants. So this is how we can tell that they definitely are variables or not. It's not so much that it's the letter A or X, it's that we're telling you we got them from separate alphabets. So if we replace in this program here, we say X is assigned 35 plus Y, then when we ask for the value of X, we get 35 plus Y. That's just the identity law in practice. What else do we know? Constant laws. If I have a constant a and I try to substitute something in, well, if it's a constant, it doesn't change. That's the rule we're trying to enforce. So, for example, 5 doesn't change if we substitute x for 35 plus y, because 5 is not a value of x. It doesn't change. This little triangle is just shorthand for yields. You'll see this in some technology books. In a programming language, we could say x is assigned 35 plus y. Then we could type in the number 27. What do we expect to see back? 27. It has nothing to do with x. So these so far meet the rules we expect. Then there's a composition law. We take the same rules we have and we just use them over and over and over again. If we have two things stuck next to each other, let's say rho and phi, and then we substitute for sigma, we should basically just ask for the substitutions of the two parts. So we could see an illustration here in code. We could have x is 35 plus 7. Then in the string x minus 5 and x plus 5, we see we get 35 plus y minus 5 and 35 plus y plus 5. The x being 35 plus y just simply went into the two locations recursively. So where does it get tricky? Well, keep an eye on this extra symbol here. That's a symbol that's going to be a placeholder for a lot of types of things that we do regularly in programs, like loops and assignments. As a technical matter, any symbols that I don't write are part of the meta language. For example, this little stroke is just notation to say I want to tell you that I'm about to substitute. The parentheses are also not part of this language. They're just things that help me explain what I'm doing. So now let's take a slightly harder version of the question. Suppose I have this code. I have x is assigned 35 plus y, and then I ask to define a function, f of x, which is going to return x times x. What should happen here? Well, with a moment's thought, we start to realize these are different kinds of x's. The x that's in here is a variable that this function will gobble up based on whatever it is at the time. This x up here is in a different what we call scope. This is trying to say that right now we want x's to be 35 plus y, but that doesn't change the meaning of the function f of x. F of x could have just as well been f of u and return u times u. The fact that we use the letter x is kind of a reuse of the variable name. It's not really a meaningful use of the value x. When we have this x inside of this function, it's local. And so we want to separate that in our substitution rules so that we can reuse our letters. The same thing happens in math symbols. The way we could write down this rule is if x maps to y, that's how we pronounce this arrow. We think of it like a movement from one side to the other. If x can be mapped to tau, then substituting for x should change nothing. This is exactly the same idea as defining this function f. The function f is now hiding behind this arrow. This next part shows it in math symbols only. X maps to x squared is saying the same thing as the function we have up here. F of x returns x times x. And we see that if we try to make an outside substitution, well, it's in a different scope. It doesn't even see the x at all. It's as if they were named different things. This is more confusing in math notation than in programming languages. Nevertheless, it still applies in both worlds. Try another harder substitution. Here we're going to try to set the x to be 35 plus y, and then we have a function which happens to use the letter y to go through some steps. We have some other variables like s, and then here we see a reemergence of the letter x. Now, we have to ask ourselves if this x is the same as that x, and we can see that they aren't. Even though now that's not part of the function f, it's inside the function, it still is playing a role that's local. We can see it's part of this loop from 1 to 10. So this x is not changing to 35y, or 35 plus y. And that's because these are not the same x. We could, in principle, have renamed them, and the rules of the program would be the same. So we want to avoid trapping our variables. This is if x is local, not even seen inside the same scope. Then when we substitute, we shouldn't do any changes yet again. So far, it seems like substitution's straightforward. You're allowed to reuse variables, and that seems like a rule that we've been using correctly. We're about to hit the hard cases. Suppose we look at this one. X is assigned 35 plus pi. Then we have def y and y plus x. It's quite similar to what we just saw, except now x is not part of a loop, and it's also not part of f. This x could really only be understood as the x that's above here. This one is, in fact, 35 plus pi. Otherwise, this program wouldn't make any sense. It wouldn't know what to do for x. Nobody here has told it what x is. So this is not a case of setting up a different variable that we could call u. This is this x. So in this case, the right way to think about it is that this x is free of any of the data in the function f. And so the rule is if y isn't visible, I'll show you what that means. There's no y up here, then we should yield the substitution of the x in the inputs right here. That's a formulaic way to see it, but I hope you can see how the technique works on the code. If you want to try this in another situation, however, it gets more frustrating. Suppose that we do put a y here. Now we've got x's on both sides, and we have a y in here. If we substitute naively, now what's going on is we've really changed the nature of the program. See, if y up here was, say, 14, now y would change based on every function call, and this would be a different function entirely. It'd be 2y plus 35 instead of y plus 35 plus 14. We need to isolate that this y is not the same as that y. This is the key problem. We've trapped a variable. So the solution is to rename the one. Since we have two different roles for y, let's rename the one inside the function and call it z. Wow. So this can get tricky, but the rules are now written and you can go through them and learn them symbolically, though I think there's going to be a simplified version I'll give you next. Here's the thing to try to look for. Most substitution is just the way you thought. Scan along, find the symbol you need, replace it with the one you're trying to replace it with. The only thing you need to be careful of is trapping a variable. Suppose I have the same x on two sides. I see the x is outside the function, that's the thing I'm substituting, and the x is inside the function, and it's visible inside the function. It's not inside of a loop, it's not called something else. So we couldn't rename it. In that situation, we hunt to see if y is also inside of this first x. Nope, there's no y visible in there, it's just pi. Visible here just means it's not a local variable. So in this case, it's safe to substitute x directly. On the other hand, in this bottom one, we see that y is trapped. It's trapped between these two x's. Here's the outside x and the inside x. If we substitute this y into here, we'll get a different formula than we intended. That's when we have to rename one of the y's. So we'll rename the inside y because that's the only one that no one can see outside of the function. The function can call this u or v or some other letter like z. Once you can rename it, you get out of the puzzle. So now let's return to how Curry and Feys hacked the constants and see why you couldn't do this nowadays with proper substitution. In this constant function becoming an identity function, I was able to see that I had two c's that were trying to trap something. But then I look back at the first c and see if it contains what letter would be trapped. That would have to be the letter x. It doesn't contain an x, so I'm safe to substitute 5 for c, and that gives me the constant function y equals 5. Meanwhile, in this one, where Curry and Feys put the variable on the lunch menu, we see that we have trapped the variable x between the two c's. Because it's visible and trapped, meaning it's not part of a local variable, we now have to rename the function's x. In a proper substitution, if we want to replace c with x, we would look at k sub c of z, having renamed that internal variable. We could then replace it with x, and then we see that it's k sub x of z equals x. Since z isn't x, this is actually a constant function. It has slope 0, but just in the zx plane. Try this slide on your own a few times. See if you make sense of it. Try to find the trapped variables and the untrapped variables. If you capture that, you've boiled down the Curry-Feys lambda calculus. So the quick history, the rules are by Curry and Feys, and the traditional notation is this lambda. Instead of the maps to arrow, we put lambda x dot sigma. This is where it gets the name lambda calculus, thanks to Alonzo Church. We've now adopted the arrows so much that it helps us draw flowcharts and future techniques like category theory, so I'll stick with the arrows as much as possible. Final recap. There's really only one rule. Substitute like normal, except if you have a trapped free variable. And then ask yourself, did you really know that before? Well, if you did, all the better. Until next time.